So our second speaker today in the Astro 3D ECR Astronomers in Australia seminar series is Isobel Romero-Shaw. Isobel is also a PhD student at Monash University. So Isobel, like Shanika, I'll give you a 5-minute warning. And if everyone could keep your questions to the end, that'd be great. Thank you.
Okay. So yes, I am Isobel and I sit next to Shanika in our office at Monash. And I'm also a member of LIGO and of OSGrav. And today I'm going to be talking to you about one very special gravitational wave event from LIGO and Virgo's second transient catalogue, which is a monster binary black hole merger named GW190521. So this event was detected on the 21st of May 2019. It happened 17 billion light years away, and it was detected by 3 gravitational wave observatories, the 2 LIGO detectors in the US and the Virgo detector in Italy. So it was a binary black hole merger, or BBH. We've got a catalogue of 44 BBH from LIGO and Virgo observations, but this one is special enough to warrant a talk all of its own because of its very high masses. It's the most massive event we've detected with gravitational waves, with components of about 85 and 66 solar masses. And when they merged, they left behind a remnant that is about 142 solar masses. And this new black hole is very exciting because it's the first ever directly detected confident example of an intermediate mass black hole. Now, I should be careful when I say intermediate mass black hole to clarify that in the gravitational wave community, we consider anything over 100 solar masses and below about 100,000 solar masses as intermediate mass. This is not true for all areas of astrophysics, but it's the definition that I'm going to use for this talk. And IMBH are interesting because they might give us the missing link in the evolution from stellar to supermassive black holes. They could also help us understand the evolution of star systems like globular clusters. They're predicted to be at the center of some globular cluster systems, and they might also help us understand things like dwarf galaxies and their evolution. So we had seen kind of hints of possible IMBH before by studying the movements of stars and things like globular clusters, so that would be with electromagnetic observations. But these observations could always be equally well explained by something else, making this the first confident and direct detection of an intermediate mass black hole. So gravitational waves are ripples in the fabric of space-time, and this is what that ripple looks like at the detector. When GW190521 space-time ripples pass through the detector, we saw this tiny oscillation, which is the strain. And it's a very short signal compared to the classic chirp signal that we saw in our first detection, 150914, which is pictured here in the OSGrav logo. And you can see that there are far fewer oscillations visible before the big peak for 190521 than there are for 150914. And the big peak is where the merger happens. So this is because for 190521, the objects are so massive that their gravitational waves don't reach the minimum frequency that is needed for them to be picked up by the detectors, which is about 10 hertz, until right before they merge. So we don't really get to see that in spiral at all. So gravitational waves are detected from about 10 hertz to about 6,000 hertz. And the human hearing range goes from about 20 hertz to about 20,000 hertz. So we can convert the strain signals into noises. So I'm going to play to you the audio of the 190521 signal. You have to listen very carefully. It's kind of like a thud, but I promise you it's the audio of the signal and not just like something falling over behind me. So listen very carefully. So if you didn't hear that, and I know it's very hard to hear, it kind of sounds a bit like somebody throwing a lump of plasticine on the floor or something. So the components are so massive and therefore the signal so low frequency that this is all we can hear at the frequencies that it was actually detected. But here is another version of that same signal. this time shifted to higher frequencies so that it's easier to hear and so that there are more cycles in band. And if you listen carefully to what I'm about to play you, you might be able to hear that the amplitude goes up and down a bit. And this is due to certain parameters of the source, which we will talk about a bit more in a minute. So if you listen for it now. That's what it sounds like. But what we actually detected was something short and fast, much more like the first waveform that I played you. So we then have to translate this signal and work out what it's telling us about the masses, spins, the distance, and the other parameters of the source that produced the signal. And this is really a problem from the analysis side of things when the signal is this short, because there's very little data actually containing the signal. So there's less information within the data for us to analyze. We can't see what's going on during the in-spiral of the system because we can't see that part of the signal. We can only make inferences about what it might look like based on our waveforms. And the shortness of the signal is also a problem from the theoretical perspective, because a signal this short can only have come from a source in the forbidden mass range called the upper mass gap. This is a place in the mass range between about 60 to about 130 solar masses, where we don't expect to see stellar black holes due to pair-instability supernova. And this is right where the source of 190521 lies. So how did GW190521 form? Well, there are two key channels when making binary black holes that merge within the age of the universe: isolated and dynamical. And I know Shanika told you about these already, but I'm going to refresh your memory and also tell you a little bit more about the dynamical case. So in the isolated channel, two stars evolve side by side until they die and merge. But pair-instability supernova seem to limit our hope for the isolated channel in the case of 190521. In our other option, dynamical evolution, we get mergers in very densely populated regions of space, like active galactic nuclei and star clusters. And in star clusters, such as globular clusters, the mass segregates. So you get a dense core full of dark, compact objects, which can interact and become bound to each other. And in such dense environments, black holes can merge dynamically. And that looks a little bit like this. So this is a simulation by Johan Samsing. It shows the kind of dynamical interaction that might take place in a globular cluster core. So it's showing a pair of black holes interacting with a third object. And when this happens, the orbital energy of the binary is lost to kinetic energy, and the separation of the binary shrinks. So as these interactions continue to play out, you'll notice that the binary orbit is getting closer and closer, as well as getting less circular. And repeated interactions of this kind can lead to a rapid shrinking of the binary. And when the binary is close enough, it merges before it has a chance to interact with something else. And this can happen very, very fast, so in as little to 4 days since the previous interaction. And you can see that it's just merged. So you've had this merger, and you have a merger remnant, which could actually, if it remains in the dense environment, with lots of other things around to interact with, become bound again and go on to merge again, giving us a hierarchical merger, in which you can get multiple generations of merger remnants merging repeatedly. And in this way, in these dense environments, we can end up with black holes in the mass gap. So dynamical interactions can give us mergers with properties that differ from the properties of isolated binary black holes, in ways that we can infer from the signal, such as its mass, spin, and orbital eccentricity. So when we have detected a binary black hole merger, we can try to distinguish its formation channel by asking it some questions. So let's ask these questions about 190521. The first question here is it very massive? Well, even just from this, yes, it looks like it formed dynamically, but that would be a very short interview. So let's keep asking it questions. The second question is, do its components have misaligned spins? So misaligned spins give rise to procession, which is a signature of dynamical formation because we expect isolated binaries to have preferentially aligned spin due to tidal effects in their stellar evolution. Whereas dynamical binaries can become bound with any spin orientation. And then because they're already black holes and they don't have tides, They retain those spin orientations, and then they have misaligned spins when they merge. And this is the LIGO-Virgo spin measurement for GW190521. So this plot shows the component spin tilt angles with posterior support intensity represented by the color of the pixel. So a non-processing system would have 0 tilt of the spin axis, but here you can see that both of the components are tilted between 60 and 90 degrees, as shown by the fact that the blue color gets a lot more intense around the kind of 60 to 90 degree mark, which means that they very much have in-plane component spins. And we can better visualize the spins through this GIF showing the measured spin directions of 1905-21. So as shown in the plots on the previous slide, both component spin axes are tilted substantially. And this causes precession, which in turn can cause the amplitude modulations in the signal that we saw before. So to answer this question, are the spins misaligned and is there orbital precession that we can see in the signal? It looks like it. But there is something else that can lead to amplitude modulations in the signal, and this is the orbital eccentricity, which brings us to the next question. Does the binary have an eccentricity greater than 0.1 when it reaches the detector? So how does this question help us? While circular orbits are typical of isolated binaries, gravitational waves are very efficient at circularizing orbits since they carry away orbital energy. Isolated binaries typically orbit each other for a very long time before they merge, so they are expected to circularize long before the orbital frequency of the binary is sufficient that the gravitational waves can be detected. In the other case, we expect dynamical mergers to be more likely to be eccentric, with about 5% of globular cluster mergers having an eccentricity of 0.1 or above when their signal reaches the detector. And this is because these binaries merge so fast after they become bound in these environments. They don't have time to radiate away any orbital eccentricity that they have when they become bound. Sadly, it turns out that modeling eccentricity in waveforms is very hard, and this often makes them very computationally expensive. So LIGO and Virgo analyses don't currently look for eccentricity because of this. However, in 2019, my supervisors and I used a likelihood reweighting method to constrain the eccentricity of GWTC1 events. So this is the 10 binary black holes in the first gravitational wave transient catalog. And to do this, we did Bayesian inference as part of this process. And for that, we used the Bayesian inference library Bilby, which was primarily developed at Monash in its early days, but is now used all over the world. So in the interest of time, I'm not going to go into the method that we use now, but you can ask me about it later if you like, or you can just take a look at the papers listed on this slide. So what we saw from these first 10 mergers was that none of them are measurably eccentric, which is entirely consistent with them being either formed in the isolated or the dynamical channel, because we only expect 5% of our globular cluster dynamical mergers to be eccentric, which means that only 1 in 20 dynamical mergers needs to be above that eccentricity of 0.1 line to be proof of the globular cluster dynamical merger channel. So if all of our mergers were formed in globular clusters, we would be due one pretty soon after these first 10 mergers. And I'm going to add our measurement for 1905-21 onto this slide now. So keep your eyes peeled, hope you can spot it. Here it is, up in the very top right. It's a complete outlier from the GWTC1 measurements. We found that 1905-21 has an eccentricity greater than 0.1 at the detector. So is this our first detectably eccentric globular cluster merger? Well, of course, there are some caveats. A big caveat for this event is that we only have aligned spins in our waveform model, so we can't measure precession. Both precession and eccentricity cause the amplitude modulations that we saw in the signal. And we actually found that precession and eccentricity can almost equally well explain the data for this event. We also tested our findings using an injection campaign, and we found that we would always confuse precession for eccentricity and eccentricity for precession for 1905-21 like events. Another drawback of our analysis method is that it is limited to eccentricities below 0.2 due to waveform limitations. So 190521 might actually be more eccentric than we've measured it to be. And it clearly seems to be railing against the upper limit of the prior in this plot that I'm showing on this slide. And in fact, other authors such as Calderon-Bustillo et al. And Gayatri et al. Have shown that this signal is indeed consistent with coming from a much more eccentric event, up to head-on collisions at an eccentricity of 1 in the Calderon-Bustillo paper. So to answer our final question about eccentricity, the evidence, if our event is eccentric, also seems to point to 1905-21 being a dynamically formed merger. So to summarize this monster event, we have seen the first observational evidence of an intermediate mass black hole, and we've actually seen it forming. This binary has evidence of dynamical formation through its procession and/or its eccentricity. So although we may not be able to decipher everything about this event just from its very, very short signal, it's given us just enough to go on that we think it probably was dynamically formed. So as I mentioned before, we expect 1 in 20 globular cluster mergers to be detectably eccentric. So we'd expect to see at least one more eccentric merger in the data that LIGO and Virgo took in the first half of their third observing run, if they are all formed in globular clusters, since we have 44 binary black holes now. And we are working on this analysis right now. So stay tuned for our results, hopefully soon. And just to finish up, here's a nice illustration of the hierarchical merger scenario where a repeated merger builds up to give us 1905-21. And that is it from me. So I will take any questions now.
Fantastic. Thank you very much, Isobel. So Anish is going to chair questions again.
As before, if there are any questions, great. Please.
Hi, thank you for a very nice talk. I wanted to ask you if you have an idea of how this can possibly, this is probably the first IMBH, right? The first possible direct detection as far as I'm aware of an IMBH. So I'm particularly interested in how this relates to the formation of supermassive black holes and whether this can shed some light on there. For sure, at high redshifts, we still don't have a clear answer. So are there constraints you can place on the formation of black holes about 10 to the 6 solar masses from what you have the observations of 1905-21?
Yeah, so as you say, this is kind of the first observed intermediate mass black hole. And prior to this event, we did kind of think that they kind of probably should exist because we'd seen stellar black holes and we'd also seen supermassive black holes. So there must be something in the middle, but we'd never seen anything like this. So in that sense, that kind of opens the door to saying, well, maybe now that we know these things actually do exist, maybe there is a way that these intermediate mass black holes somehow accrete mass or merge and undergo repeated mergers and build up into supermassive black holes. So this is actually, yeah, it's really exciting from that perspective, because if we had never seen an intermediate mass black hole, we would have to rule that out and say, well, it's very unlikely that supermassive black holes formed out of these things if they don't seem to exist in the universe. But now that we have seen them, we can start saying, well, we've seen evidence of this thing, so it must exist. So therefore, is there another thing like that it's going to merge with and then in many millions of years become a supermassive black hole later on? So yeah, there are kind of exciting prospects for supermassive black hole formation from this event.
Great, thank you.
Are there any questions? Please feel free to raise the hand or ask the question in the chat.
Hi.
Hi.
Yeah, great talk.
Thank you.
I want to ask, I saw that you're giving preference to globular cluster in your models for finding these mergers. Yeah, just wanted to ask why not nuclear clusters, which are more dense and highly active?
Yes, that is a very good question. I am putting preference on globular clusters in this talk and in my kind of comparisons, because those are the things that we have quite a lot of models of and results for. People are starting to now look at things like nuclear clusters and AGN for sources of eccentric mergers, and also things like 190521, which are more massive. Because one of the problems with globular clusters is that they don't necessarily have high enough escape velocities to retain black holes after they merge. So after you merge two black holes, they generally get quite a high kick, and it usually kicks them out of a cluster if it doesn't have a high enough escape velocity to contain them. So things like, as you said, a nuclear cluster or something like an AGN has a much higher central density, so it more easily retains these things. So you more easily get these hierarchical mergers and potentially eccentric mergers and potentially very massive things. So there's a lot more work now, I think, going into looking at other kind of areas of dynamical formation.
Right. Are there any further questions from the audience?
Can I ask a quick follow-up question to that one, Isobel? You mentioned AGN as being a source for these dynamical evolution. I'm trying to think how that would be the case. Do you mean a galaxy that hosts an AGN, or do you mean the merger occurred close to the center of a galaxy?
Yeah, I kind of mean close to the center of the galaxy, because obviously there's a lot of stuff there. There's a lot of things getting captured there and kind of hanging around and interacting with different things. So there could be cases where something is perhaps orbiting within that kind of area, and it would then kind of act a bit like a star cluster and be this kind of dense area full of stellar material and stellar remnants where something could merge dynamically.
So does it need to be an active galactic nucleus, or can it just be just a the central region of a galaxy?
It can just be the central region of the galaxy, yeah. I think so. I'm talking about AGN because I think there was an electromagnetic counterpart proposed for this event, and people have been talking about how that could possibly happen. And AGN was proposed as one of the potential possible formation scenarios of that electromagnetic counterpart.
Right, thank you.
Yeah, I had another question.
Yeah.
I wanted to ask about these dynamical formation channels. So in cases of these, so there are preferred ways such as the 2+1 interactions for the binary and the single. And do you have any idea of like what kind of fraction or other preferences could be, such as single interaction or other interactions, and which one some other ways these interactions can happen and these binaries can form, and what are like the weightages or like the fractions for these kind of things?
Yeah, that's a great question. So there has been work into this, because obviously you get single events and you get single captures, which is when you get two black holes kind of just rushing around inside the globular cluster or wherever they are, and then they just happen to brush so close to each other that their instantaneous gravitational radiation causes them to merge without really any kind of without really too much inspiral first. So you do get that. But the cross section for that is quite small, because these are just kind of single black holes, whereas the cross section for a binary is larger, which brings me to kind of the next point, which is about like 2+2 interactions, which should kind of be less common than the 2+1, but because the cross section is larger, you can actually get rates that kind of rival your 2+1 interactions, depending on how you set up your simulations. If you actually are interested in that, I can find some papers and send them to you if you give me an email address, because there is work into this and looking at kind of the ratios of the rates.
Yeah, I would highly appreciate that, since I'm looking into the same kind of area for my. Yeah, awesome. I'll put my email address in the chat. Yeah,
sounds good.
Thanks for that.
Thanks.
Fantastic. Just wanted to point out that Shanika as well has shared the link to the paper that she presented for those that would like to check it out. Yeah. Are there any other further questions? If not, we can move forward.
Okay, well, if you think of any more questions, you can feel free to email both Shanika and Isobel, and I believe they're both on Twitter as well, so you can find a way. So please join me again in thanking our speakers for today, both Shanika and Isobel, both very fantastic talks. I learned a lot. Please also help me thank my co-host, Anisha, today, and thank you to all of you for listening in. So.